Hello everyone, my name is Nadi. I'm a researcher at Delft University of Technology. In this video, I briefly explain the optimization and network models, as well as all sorts of models developed in the LEAD project that facilitate a simulation environment to help decision makers assess different policies in the urban logistics. In this lecture, I will first introduce optimization model developed within the LEAD project. Then I will explain the role of network models, and finally I will touch upon the impact assessment models within the LEAD framework. For an agent in the system, optimization models are basically iterative procedures that solve the problem of decision making by minimizing a cost function. The cost function is mainly associated with the simulated cost of applying a decision variable in the simulation environment by an optimizer, taking into account all sorts of inputs and constraints that exist in the simulation environment. Each decision problem that an agent encounters in the simulation has different costs, inputs, and constraints. The output of the optimization model can help policymakers to identify the total cost of the system. There are mainly 3 optimization models developed in this project, that their inputs and constraints and all components depends on the nature of the problem. These 3 models are joint replenishment and delivery problem, 2-echelon capacitated location routing problem, and planning city logistics systems. Each of these models are developed to model the interactions between agents in the system. Looking at the urban freight system, we can identify 5 agents that interact with each other to facilitate delivery of goods from shippers to the end users. These agents are shippers, warehouses, transport service providers, shops, networks, and customers. The decisions of another 2 agents, namely the environment and public authorities, also exogenously affect the system. The first optimization problem, which is the joint replenishment and delivery problem, models the interaction of shippers and shops. Shops have to replenish their stock in order to be able to satisfy their customers. The larger quantity of shipments that they order from a shipper would reduce their transport costs. Therefore, shop agents have to bundle their shipments by choosing a larger shipment size. However, ordering a large shipment size will pose large inventory costs. A trade-off between these 2 costs can be found or identified by the joint replenishment and delivery problem. Another interaction that takes place between multiple agents is between shippers and transport service providers and warehouses, where shippers have to decide whether to send their product directly to the shops or via an intermediate warehouse. The benefit of intermediate warehouse is that the shipper does not have to stop their production line due to the low capacity of stores in the manufacturing site. Therefore, their cost of production will be reduced by continuously keeping the production line working. However, the intermediate warehouse would add to their inventory cost of a shipper. It also has an extra trip to the transport and hence pose extra costs. It is also important to identify the location of the warehouse to which the product has to be stored. A trade-off between all these costs can be made by the second model in the list, which is 2-echelon capacitated location and routing problem. Finally, the third model in the list provides the system with functionalities of routing and scheduling of trips between shops and customers, which take place by transport service providers. It includes route choice and time of day scheduling of trips that have to take place between pickup and delivery points. Now let's briefly talk about the network models. The network models specify the interactions between the service providers, road networks, and public authorities. We have two network models, the first of which is the TU model, which generates traffic and distributes the flow over origins and destination, taking the delivery tour and time windows into account. The second model is a traffic assignment model, which assigns traffic to the road networks. Any interventions defined by public authorities like zonal restrictions or traffic management can constrain the decisions of transport service providers while they're planning their delivery tours. The network model developed in this project can help us to identify traffic intensity or congestion on road network due to the delivery of goods in a city logistic. LEAD also includes 6 impact assessment models that helps decision makers measure the impact of a policy. These models are greenhouse gases model, a vehicle emission model, protocol and regularities to calculate the impact of externalities, multi-criteria decision making, Monte Carlo simulation for environmental impact, and police model. The components of these models depend on which externalities they measure. For instance, air pollution, emissions, congestion, so on and so forth. These models assess the impact of decisions made in the system or by public authority on the environment. The result of these impact assessment models are basically measures of the externalities, such as greenhouse gases, emissions, any sort of emissions, or some sort of indexes that condenses the performance of the system. These indexes can be specific to a particular model or some other well-known indicators such as the social cost-benefit analysis ratio. Well, that was a brief introduction of all the models regarding optimization, network models, and impact assessment models, which has been developed through the LEAD project. For more information about these models, feel free to approach us by any means of these communication channels listed here, either by my email address, website of the LEAD project, or LinkedIn of the LEAD project. Thank you very much.